And just forward, about 3 years ago at the NSF, formulate that idea of what I'm going to talk about very vaguely. But we needed 3 years through the Yangtze program, or the studies that we had, to, to this day, to be more confident in that we could use TL thermoluminescence to say something about how long the lunar surface takes to equilibrate or be at a certain temperature. So that's what we're going to talk about in this presentation. There you go. TL is a really niche thing. I'm probably the only one that's looking at doing this for lunar science. And just to explain what we're doing or what's happening is that any material, especially lunar regolith in that case, absorbs the ionization radiation on the moon. And what we're showing up in here is a kind of like a diagram of steps. In the first place, what you see is we have that radiation, it's hitting the electrons that actually get promoted into a higher energy state, so being ionized, and they get stored in here at different traps or levels, essentially. And if you put some heat into the regolith, it actually gives the activation energy to let them fall out. And then while they're falling out, they're producing actually that excess energy, they're giving it off as light, and that's what we can measure. So if we're heating up a sample, and we're looking at the light that's coming off, we can measure the thermoluminescence. And down here is just the equations that really correspond to it, the buildup over time, and N is the number of traps that are filled. Depends on like a coefficient of how fast this actually can build up, and the radiation dose. And we know that for the lunar equatorial region fairly well. And the decay also depends, that traps depends on the time. Over time depends on two really important parameters I'm going to talk about that we really figured out through the Yangtze work. Is E, that's the kind of like trap that's present, and also S, which is, in the simplest case, a frequency or probability of that process to actually happen. So what does the glow curve look like? So if we're looking at something that comes from an illuminated surface, it looks like this. What we're having is the temperature of the sample that it's been heated to and the light intensity it's coming off. And this is what we call a glow curve. And what we're looking at this is that we actually see there's like, I'm plotting two areas in here, which we call, those are the individual peaks or the individual actually traps that were being filled. So there's two traps that are actually stable at that temperature. Here is more the general equation for it. And we're really looking at the, like E and S. That really depends on where this peak is sitting, and the intensity of that peak depends on how many traps are actually filled. If you're looking at something that comes from a colder region, let's say the Apollo 17 Station 6 boulder floor shadow, we can actually see that the glow curve will be looking different, and that's the reason it is because that sample was colder. Some of these lower energy traps were actually stable and could build up over time. And when we're irradiating a sample at room temperature, we're having a total of 8 peaks. That's really what's coming out of the Yangtze studies is we are finding that there's 8 discrete peaks from room temperature up to 800 degrees Celsius that are in typical lunar mare and highland material. So what can we actually do with these peaks? We can rearrange equations and we can come up with the equilibration temperature that sample, that peak would represent. And this is where these temperatures actually come from. We can say that based on these peaks, the sunlit surface is about 370 degrees. And from that shadowed boulder area, this is about 266 plus minus 10. So we can also infer like how long that, or we can calculate how long that buildup will take, or what we are measuring, how long that would have taken. In that case, our results suggest that was about 50,000 years. So all of that really got us the idea, okay, we can actually do some really cool work for equatorial regions. How can we actually use that now, knowing that Artemis program will go to colder places? Like, what can we do with this? So what we really want to do is confirm that there's any low temperature TL. That's really the first thing that we want to explore. And then, just the same thing, determine what the peaks are and how many are there, and then use those, derive the E and S parameters to use them in these calculations. So here's the thing. So what I'm showing up in here is two plots. It's the peak temperature of that area that you showed where the maximum was for all these little peaks against the E value. And that's coming out of the ANSYS study. Is that we're looking at this, that, for now, we'll just assume a linear relationship in here, but they're all lining up in here. So that means if we're going to colder temperatures, where, in the glow curve, there's actually room for more traps. They're just very low energy. If we're looking at S, same thing. In here, that's then basically the magnitude of that S value against the peak temperature. You also can see, just extrapolate that there's room for S parameters. And that's basically work that's currently in review coming out of our ANSYS studies. So if we're thinking about lunar cold traps, temperatures around maybe 100 degrees, make it easy, we would expect that there's traps with an E value of 0.4 and S value is somewhere around 10 to the 15. There was only one study done many years ago, 72, where a group of researchers actually looked at one sample of Apollo 15 find. They had the capability to actually irradiate that sample at 80 K using liquid nitrogen and irradiate it at that temperature and then switch on the heater and look if there was light coming off. And that's really the only cryo-TL glow curve that we have. And there is evidence that there is peaks. We have been fitting those data. It's a larger area. There's a lot of uncertainty if we did it right. But it suggests that there is something actually there. So the motivation here now was, I want to know, at least to some degree, if there's TL. I actually want to measure it. So I just put, it's 3D printed, essentially, a little device that can go below room temperature. Not much, though, but at least something that we just can confirm in ourselves that there is a there. So what it really does is it's a TAC or Peltier cooler sitting underneath here that is sandwiched on top of a little heater, and then I just covered everything in copper foil because the material itself would be luminescing as well. So just blocking that off. And
3 minutes.
Okay, thank you. And what we're doing is we're sliding over there's a sample actually sitting there with regolith or simulant. We're sliding over the X-ray tube, irradiate it, 30 seconds, slide it away. Here's actually the PMT, hard to see. Slide it on, it's all covered, so there's no ambient light in that whole system, and switch it on. So that's what we see. We started off with a simulant, just, it's an expendable sample. We can't really do anything wrong. That is when we do it at room temperature, and this is when we actually have it cool to about 220 degree Kelvin, and there is extra TL there. If we're doing fitting, we can actually see that there's about 3 new peaks that have appeared that we didn't know about. And then just recently, we expanded to other kinds of samples, so Apollo 17 samples. The valley floor has kind of like a Mare type of sample, Station 2 foothill sample as an approximation for highland material that we would expect at the lunar South Pole, and then also an orthostatic regolith breccia. And they all have TL. They all look a little bit different. They actually normalize to 1 just to call out the kind of different shapes, but there is TL. We can find it. And these values range are shown down in here. I just printed out, but just graphically, this is where they plot. So actually, independently, I just found out that these actually extend to what we had found before. So that was very encouraging. So what do we do with this? We can now use these trends that we have and predict, okay, let's assume we want to look for water. Let's assume 110 degrees Celsius is kind of like the maximum that we want to have. We would expect to have a peak around with an E value of 0.55 and S value of 1 to the 15th, really. So what we want to do is, and this is a plot of where that peak position is, and using that equation down here to come up with like a temperature estimate. So this is what we would want to expect as a peak with their characteristics to have. All right, wonderful. And yeah, if you plug those values in here, this is, like it takes a lot of time to build water up on the moon. So what I'm really doing in here is plotting the number of traps that would be filled using these parameters in terms of over time. So this is in millions of years. So this is 1, 10, 100, and then, that's the end right here. So if something would be at 95 degree Kelvin, a PSR, it would take about, this method could give you something about 1 million years. If it would be even colder, you could extrapolate that, the maximum time that this would take maybe 100 million years. If you use different peaks, you can actually, these equations arrange, these lines change depending on the temperature that we have. So to come up with the end, more time maybe? Okay, I wasn't quick, but we can do something with this. So that's our plan forward. I actually want to build a facility to do that kind of work to explore this even more. Thank you.